in University College London, and then he was a postdoc in Montreal. So we were just exchanging notes because I was also in University of Montreal. He was in a Center for Mathematical Research, CRM, a great place for doing research of mathematical physics type. Now, even over there, he had an interaction with many people, including part-time faculty in Concordia University. And Montreal has a very good atmosphere for science, mathematics, and for example, Jerry Brassard. I was talking about BB84. He is in Montreal and with the University of Montreal. So that's a great place to, for example, this time, this big award, for Google deep learning, that neural network kind of thing, was to University of Montreal. Has a huge tradition of mathematics, mathematical physics, and many other things. Great center for learning, lovely atmosphere. A lot of few people who are young should keep Montreal in mind. Of course, UK, is a great place, also. So he has the experience from both the sides. And then he has come back as a faculty to Mohali, and he has interest in quantum information, then PT-symmetry. You might be thinking, why PT-symmetry? Now you realize PT-symmetry has opened a big way to do things which is not allowed in quantum mechanics. I told you, quantum mechanics are lots of constraints. You cannot copy, you cannot xerox, you cannot erase. PT, and you have to do everything in transformation. PT-symmetry, of course, you can realize in some design systems. Now he's talking about cavity optomechanics. So there, amazing flexibility is there. So now, great thing is that in optics, they are realizing PT-symmetry everywhere. So young people keep in mind that PT-symmetry is being used to produce more powerful lasers, come up with faster algorithms. So it's worth listening to, which way we can use it. It's a very new area. So it's quite nice that Sanjeev has picked up this thing for us. So Sanjeev, the stage is yours.
Okay, thank you very much for the introduction. Of course, many thanks to the organizers and Professor Panigrahi for the opportunity to talk here. So many nice talks are going on in this platform, so it's a real pleasure actually for having the opportunity to talk here. So yeah, since Professor Panigrahi has already told a bit of my research areas and about the topic of the talk, so I would like to start straight away without the introduction because it is already mentioned quite elaborately. So this will be the outline of my talk. Three main things I will cover. The first one is quantum resource theory of non-classicality in generalized framework. Quantum resource theory is actually a very new subject area. Actually, I would say most of the good papers are coming in last 3-4 years. So it's a very new and dynamic area. It will be clear after I talk about the details of that. And the second aspect, I would like to talk about the optomechanical understanding for generating those lights. Usually it is very useful for many other areas, but I will only focus on the generation of the non-classical light using the optomechanical systems. The third one is the PT-symmetric non-Hermitian systems. I will start with a brief introduction of that, and then we will focus on the understanding of open quantum systems using these models to understand the entanglement rebirth, which is a very relevant problem in quantum information science. Okay, so the first thing is the resource theory. To understand what is resource theory and why is it important in quantum information theory, let me start with a brief introduction of this thing with an example to entanglement. So entanglement is called as a resource of long distance quantum communication. So what is it? Basically consider that Alice and Bob are separated at long distance in space, and each of them owns quantum lab. So they can do any kind of quantum operations they like but that has to be local operations. So they can do any quantum operations on their own lab, but they cannot communicate that state to each other because there is no quantum channel available. So the only communication mode is the classical channel, like a telephone. So it means that we are giving some free operations to these two people, which is called LOCC, which stands for local operations and classical communications. So that is what is allowed. They can do some local operations in their lab and they can communicate classically. So obviously, it is not possible to communicate a quantum state based on these free operations. There is no way that we can do a quantum communication. But suppose someone provides an entangled state to them, then it will facilitate a quantum communication between these two bodies. For instance, Alice can teleport a quantum state if suppose there is a maximally entangled state, which is let's say one of the Bell states. Then with respect to that, Alice can set up a teleportation, send it to Bob, and then Bob can do some local operations and then send it back to Alice and so on. So this whole communication process is facilitated by the entangled state. And that was not possible to produce by any of them, but it was supplied from outside. And that's why the name is called the resource. So that means it has to come from outside because it is not on their list of free operations. If we can find such a thing, that will be called as a resource. Let us try to understand a bit more technically in terms of non-classicality. So let us consider that there is a set of coherent states C, and we define a set of operations O with respect to that set. Okay, and that operations let us restrict in this way that there are some free operations F belonging to the operation, the set of operations, and consider that any state rho, if that belongs to the set of coherent state, then this operation operating on the state will always be in the coherent state. So what I'm trying to say is that if I define a set of operations in such a way that we cannot go to a non-classical regime by operating that operator on the state, if the state belongs to the coherent state. So we have no option to create a non-classicality from a set of coherent state, in short. After defining this operation, we can also define a non-negative measure, let's say M rho, and we define it in this way that if the M rho is positive, then it goes to somewhere else, which is basically non-classicality in this scenario. But if it is 0, then it's a classical state. Okay, we don't know what is this measure. Okay, this is just, we are saying that suppose we can find a measure for that, for which this property will be satisfied. Of course, there will be two more properties, very important properties. One is the convexity. That means that we cannot increase the coherence of or non-classicality, any property you want. We cannot increase it by mixing the states statistically. Okay, and the second thing is monotonicity, which says that even if we do this operation, the F is the free operations we have. Now, if we operate this on the state, the measure will never increase. It will always be a decreasing function. So overall here, what it means that we wanted to define a measure which will not allow us to go from a coherent state to non-classical state. If we are operating on the coherent regime, it will always be within the coherent regime, and we have no option to create a non-classical state. Now, if non-classicality comes from somewhere outside, then that will be the resource for our purpose. Okay. So now consider that there is a quantum optical state rho. I don't know what is the state, and I know the measure. Suppose I have calculated the measure, and I apply this measurement on the state rho, and I get a positivity, then I will say the state is non-classical. Okay. Obviously, one can compare different non-classical states and compare their non-classicality. Which one is better resource for non-classicality? That is very simple. Like we measure the, we take the measure on the, both of the states, and whichever is higher, obviously that will be the better resource for our understanding. Okay, I think it will be even more clear if we come to the examples. So here are three different measures I have written. The first one is the negativity of quasi-probability distribution. This is a kind of a general S-parameterized probability distribution in terms of this measure, where S, if it is 1, then it is called a P function. If it is 0, we call it a Wigner function. And for 1, it's a Q function. Now, it can be shown, actually it has been shown recently, that the measure, the non-classicality measure for a particular state rho is actually higher for the P function measurement. And obviously, this way, this is a P function, this is a Wigner function, and this is a Q function. So it clearly tells that we don't need to even actually look at the Wigner functions or Q functions. So it kind of unifies the three quasi-probability distributions. If we can calculate the measure for the P function, that will be enough, because that will already tell that the amount of non-classicality it has. Also, the P function and the X quadrature variance, they can be related to each other. And if the P function is negative, then obviously we have a quadrature squeezing. So this again tells us that we don't even have to look at P function, because calculating the P function for a quantum optical state sometimes is very difficult. So rather we can just look at the quadrature variances, and that will suffice. So then we have to look at a measure for the quadrature squeezing, and that measure is very simple, and it depends on the ratio of these two things, delta x phi square and delta x phi square vacuum. So if this ratio is minimal, which will be the maximal quadrature squeezing that we will obtain from this scenario. And obviously, if it is 0, then it's the maximum one. So we want that this variance is very low. If this is minimum, then we have a base quadrature squeezing. Another measure, very well-known one, is the sub-Poissonian photon statistics, and it is very similar to quadrature squeezing. Again, the measure is dependent on the ratio of these two quantities, and incidentally, this is just negative of the Mendel parameter. We know that Mendel parameter is a very known measure, and if Mendel parameter gives a negative value, then we can always say the state is non-classical. Since our measure, we have defined it as a positive measure, so it's clearly just a negative of the Mendel parameter. Okay, so we will use these measures for a bit more analysis on the resource theories for generalized lights. Here is an example, which is called the generalized squeezed state, and the solution of the state is given here. Of course, the construction procedure I didn't go through, but if someone is interested, I can of course discuss that. So first thing is to note here is that the state, the squeeze state we have constructed here, is not the usual harmonic oscillator squeeze state. It is slightly different, and it is actually more general in the sense that this function in the denominator fn, that is a general function. Okay, so that means if a general class of, let's say, a general potential, quantum mechanical general potential is supplied, then if I can calculate the function, I can construct the squeeze state for the system. Okay, it's a very difficult one to solve, to obtain the general expression of the squeeze states for a general function, and you can see it's very complicated. So this function Fn is extracted from the eigenvalues of the system, provided that we can factorize the Hamiltonian in terms of the generalized ladder operators. And if we can do that, then of course we know the Fn, and we put it here and we get a generalized squeeze states. Here I have taken a post-Taylor model as an example. Of course, anyone can take any other model and verify that this is working. And we have shown that the post-Taylor potential applied on this definite or on this solution is actually giving non-classicality, and that non-classicality can be detected from the negativity of the Wigner function we have plotted here. Of course, there are other analyses available in this paper, but those let us skip for this moment. There is another interesting component in quantum optics is the Beamsplitter. So Beamsplitter is a nice device to check whether a state is non-classical or not, in the sense that if we have coherent states through the inputs of the Beamsplitter, we always get a coherent state in the output. Maybe their intensities will be redistributed, but we will always get coherent state at the output. Now suppose we send non-classical state through one of the inputs. Then we will never get a coherent state at the output, but the output will be entangled. And this is why this Beamsplitter technique is very important in quantum optics. So here is an expression. This is the squeeze state. I'm sorry. So this is the squeeze state that I have shown in the last slide. This is the generalized squeeze state. Now we apply the squeeze state through one of the inputs, let's say through the X. And in the other input, we just send a vacuum state. And this is the output that can be calculated theoretically by considering the Beamsplitter operator, which is a muted operator. And let us try to see, analyze what is the output. And this is done easily by using a linear entropy. And here are the plots. So in the left one, we plot the entanglement entropy for generalized squeeze state, showed by the purple line, and the orange line shows the standard harmonic oscillator squeeze state. So it is obvious that one new thing, that the generalized squeeze state is actually producing more non-classicality, or let's say more entanglement. These are the two things that go synonymously in this, of course, in this scenario, Beamsplitter scenario only, but not in all cases. So here we see that here is clear advantage of using the generalized states. And moreover, in this figure, we plot the entanglement with respect to the parameter tau. This is the parameter that is the coming from the generalized models. And we see that if we can set the parameter properly, we can increase the entanglement even beyond what we have here. So we have a special control here over the parameter in case of the generalized state, which was never there in the harmonic oscillator case, because harmonic oscillator will always give you a constant value irrespective of whatever you do. But here we have a freedom, and that freedom we would like to use. Here are some other examples. I will not go through all the details of these examples, but just giving some overview. So for instance, here we considered photon subtracted squeezed vacuum state, and we plot the Wigner functions for those states, and they are showing the non-classicality clearly. But more important things are here. For instance, here in the sorting even cat state, the red dotted line that shows the harmonic oscillator even cat state. That's the number squeezing we are studying, of course. And we see that harmonic oscillator states there is no number squeezing because it doesn't go to the negative region. Whereas in the generalized case, all the different values of parameters, they always show a good non-classicality in the sense that it reaches -1, which is the maximal amount of non-classicality that can be generated, and they are hitting that maximality. So obviously we can see that the generalized cat states is giving some advantage here. And similarly for photon-added coherence states, the same color lines show the comparison between the harmonic oscillator and the generalized photon-added coherence state. And there are 3 sets of values. And you can see that always the solid lines are below the dotted lines. And the solid lines correspond to the generalized one. So it's clear that different kind of states that are giving good resources of non-classicality. Here is an example also for atom laser. So atom laser is actually slightly different, but it has many importance in actually increasing the accuracy of different interferometry experiments and so on. But we will not go there. We'll just try to understand what is atom laser. So atom laser is a kind of a light atom interacting model. Consider a 2-level atom where the Bose-Einstein condensation happens at the ground state. And suppose I send a optical light, laser light, in resonance with this atom. So then at the resonance, there will be a coherent atomic laser beam that is coming out of the system. And this is an experimentally got result. This is a very famous result. So obviously we get a coherent atomic. Now, obviously we know that the atom coherence doesn't help always, particularly if you want to look at the quantum sensing experiments like gravitational wave detections and so on. In those cases, we know that having a non-classical light is more useful. So let us try to see if we can get a non-classical atom laser beam with a generalized non-classical light. So what we did, we sent a generalized light that we have constructed previously and make it in resonance with this atom. And in that case, we see these Mandel parameters. The number squeezing pattern is actually hitting the maximum non-classicality again. So that is indicating that the non-classical atom laser may be constructed from the generalized classical light. If you want to understand the Hamiltonian, it's pretty easy. It is usual like the way we derive the Jaynes-Cummings Hamiltonian. This is very similar to that. This is the light mode, A dagger A. B dagger B is the atomic mode, and this is the interaction one where capital omega represents the interaction strength, and NC is the number of atoms in the Bose-Einstein condensate. We have to take some approximations. It's very difficult to solve the exact Hamiltonian, and those approximations are standard. The first one is the Bogoliubov approximation, which tells that the number of atoms in the condensate remains almost constant throughout the process. And the second one is the rotating wave approximation. This is taken when we consider any resonance phenomena. We generally neglect the highly oscillating terms and try to linearize the Hamiltonian. And that's what it is done here. This is a linear Hamiltonian. So theoretically, this is very fruitful to study the generalized states. But the bigger question will obviously arise, whether can we generate these states or not? Because that's the question that finally we have to think about. Okay, it's a difficult question, as you can understand from the framework, but we will try to show some indication that it may be possible in near future, and some results are already shown here. So there is one thing which is called nonlinear non-classical states. Those nonlinear non-classical states are nowadays more or less possible to obtain by using different systems. Like here, this is a simple one using a car type nonlinear cell. If we send a laser light through a car type nonlinear cell, we get a squeezed light at the output. Of course, the amount of squeezing we get from this scenario is very, very little. So that's why people have thought of different complicated type of circuits to make the squeezing more for the nonlinear states. Here are two different setups. There can be many, but just for an example, that we can put it in the Mach-Zehnder interferometer, put the car cell in the Mach-Zehnder interferometer, we can get better non-classicality or squeezing, or we can have some complicated circuits like that to prepare the nonlinear states. But the state we are talking about, they are slightly different from the nonlinear states because they are model dependent. Remember that there was a function, Fn, general function, and that depends on the particular model. If the model is not nonlinear, obviously we cannot use these techniques. So we have to be, we have to get something very model specific. And that's why we will talk about the optomechanics. So optomechanics, the concept is very simple, is that suppose there is an electromagnetic wave interacting with a large massive oscillator, and we want to study this oscillator in the quantum regime, and we want to see what is happening. That's what is the optomechanics all about. And the simplest demonstration of optomechanics is that you send light and let it interact with an oscillator and then let it come back. But here the amount of the interaction or the radiation pressure we get, this is very little in this one interaction. And that's why the concept of cavity optomechanics comes out, where we can send the light and then let the light interact between the two mirrors multiple times so that we can have a good amount of radiation pressure in the movable mirror. Okay, so let us try to see the theory, at least to understand it. It's very elegant and useful. So first of all, we consider the closed optomechanics. That means we are yet not considering any coupling of the system with the environment. None of the modes are coupled. There are two modes here. One is the cavity mode, one is the mechanical mode. And we have to take the interaction between these two. Okay, and the Hamiltonian, we can take the cavity mode, the usual one, A dagger A, and the mechanical mode is B dagger B. But then to have the interaction, we can use this trick. We can say that the length between these two mirrors is obviously varying because of this movable mirror. And if length varies, then the cavity frequency will also vary accordingly. So that's why here we have cleverly put that, this omega cavity, which is a function of Z. Okay, and since we can consider that the frequency is changing very little, we can take a Taylor expansion and that we can put in the Hamiltonian, which will generate the interaction term in this scenario. Now, to understand how much interaction is happening here, that can be understood from this constant Z0, which is the single photon optomechanical coupling constant, and that can be represented in terms of the 0-point fluctuation of the mechanical oscillator. Okay. So, for example, if we take the 0-point fluctuation of the order of nanometer, that corresponds to a mass of 1 atomic mass unit. So consider that the oscillator here is very light. Its mass is 1 atomic mass unit. Then the amount of 0-point fluctuation that will be created is of the order of nanometer, And so G0 will be of the order of that one. So it's a very little amount of interaction that is being created here. Now, obviously, the practical scenario is that the oscillator is massive. It's not so light. So if we take 10 to the power 12 number of atoms here, then the 0-point fluctuation will actually increase by 6 order. So it's like 10 to the power minus 15 meter now. And the interaction is even more little in this scenario. So this is actually very little. But there is also this A dagger A. And obviously, if we have more number of photons here, that will increase the interaction. And that's why we want a huge number of photons to be stable within the cavity, large, usually of the order of 10 to the power 8 number of photons we will consider. Right. But this closed optomechanics is just an approximation, I would say, because anyway, we cannot isolate the systems completely from the environment. They will obviously couple to the environment. So consider that both modes are coupled, both the light mode and the mechanical mode. And in that scenario, the dynamics will be given by this master equation, where the first part represents the coherent evolution and the second part is the dissipative evolution. And the calculation of dissipative evolution is slightly complicated. I will try to avoid that, but here are the results I have put. For instance, for the mechanical mode, I have this much of dissipative term if gamma is the decay rate and n bar is the mean Bose-Einstein operation number. Similarly, for the cavity mode, we can get the result, and obviously we can write down the master equation. But one thing is important, we need a cavity driving. For instance, here it is shown, we have a signal laser here. But since this mechanical mode is actually decaying and the optical mode is also decaying, so if we want to maintain a constant number of photons within it, we have to have a pump laser. We have to have a kind of a driving from outside so that the system stabilizes. And that driving Hamiltonian can be written in terms of the omega L, which is the frequency of the light. So that the master equation contains, so first of all, the Hamiltonian will have this A dagger A, B dagger B, which was there from the beginning. And this is the interaction term. And the third one, and the last one is the cavity driving. And here we also take the contributions due to the dissipative evolution. The problem here is that, look at this part here. This is not quadratic Hamiltonian. There are more than 2 creation and annihilation operators. So it is actually a difficult problem to solve in quantum optics because it's a non-quadratic. So we have to make it quadratic in order to solve the system. So the first thing we can do is that take a rotating frame. This is very usual in quantum optics. Then you take a unitary transformation of your density matrix and you go to a new frame where the time dependence simply vanishes. This is an advantage for us because time dependent Hamiltonians are not easy to solve. So the rotating approximation makes the Hamiltonian time independent, and then we will write down the equations of motion, one-term Langevin equations in this scenario. So this is also written in the rotating frame. Subsequently, we can take the change of variables and then rewrite the equation of motion. Of course, when we are changing it, we have a lot of terms proportional to alphas and betas, and these are the terms that are coming extra. So let us try to throw them out from the equation of motion. So we make it 0 and try to solve this equation. This solution usually is bistable, but we can have a stable solution if we choose this delta 0. The detuning is of -3/4 kappa. So we will stick to this solution and rewrite the equation of motion here. Now we can see that this equation of motion is still, we can neglect the last two terms here, because alphas and betas have to be much larger than 1 if we want to have a higher driving. We need a higher driving in the system to maintain a constant number of photons. So alphas and betas have to be greater than 1, and if they are larger, then obviously the last terms of these two equations are very small compared to the others. We can simply neglect them, and this is what we get the equation of motion, and this is the Hamiltonian. Okay, so here we can clearly see that the Hamiltonian does not have any non-quadratic terms, but they are simply quadratic, and things are pretty easy now. Equations of motions are easy to solve, so we can have solutions out of that. And this is basically the first equation you will see in any optomechanics paper that will come out, that you see this Hamiltonian and these equations of motion. But here you do not understand these detunings and so on. That's why I just thought of explaining all these things. This is the procedure that we have to do in every time we want to study the quantum optomechanics systems. If anyone wants to look at more on this thing, one can look at this review paper by Aspel-Meyer's group. Okay, so some of the applications. These are mainly applicable for coupling different degrees of freedom. For instance, here we have a microwave mode here generated from the LC circuit, and we have an optical mode here. If you want to couple these two modes, then you simply put a bar here which is movable, and then you can couple these two degrees of freedom using this optomechanical system. Similarly, a qubit charge coupling can also be done. Here you have a charged mechanical oscillator, and you put the qubit within the Fabry-Paro cavity, and these two degrees of freedom will be coupled. And also qubit and light coupling can also be done, and so on. There are many applications. More relevant applications for our purpose is the generation of squeezed state using the optomechanics. So here the setup is that you have a Fabry-Paro cavity, and you put a membrane, a thin vibrating membrane within this, which will interact with the light, and it is shown that the light will be squeezed. A very good example is the LIGO experiment, which is possibly the best example for optomechanics experiment, where you have this cavity, and any incoming wave, gravitational wave, will interact with the light within these cavities, and they can be measured. The interaction can be measured with a very high efficiency, as we know from the LIGO experiment. Similarly, entangled state can be prepared using quantum optomechanics. It might be needed that you need more number of cavities. These are the two optical cavities. You entangle, you couple it with a mechanical degree of freedom to generate the entangled light, and so on. Of course, here in the mechanical mode, we have to cool this, because see, there are certain things like we need to remove the errors, or let's say the thermal excitations, the excitations, any noise that is coming from outside, like thermal noise, we need to take it out. If we want to take it out, we have to put this mechanical system into a cool environment so that the thermal excitations are taken out. Of course, the cavity modes, like the optical modes, that can be done in the room temperature, because any optical experiment does not need a cool environment. So therefore, you can put the mechanical one in the cool environment and the optical modes in the standard environment, and couple it to get the entangled states and so on. Okay, now I will come back to what I was trying to say is to generate the generalized non-classical state. Consider here an example where the commutators are not the usual quantum mechanical commutators, but they are, let's say, a deformed one. But this is just a demonstration purpose. One can use any other generalized quantum mechanical model. But suppose we start with this configuration, and then the optomechanical displacement operator we can write as an unitary operator which will displace the optomechanical state in the phase space. Here we have these mechanical operators x, m, and ym. This is a two-dimensional oscillator, so we will have both these freedoms. And NL is the number operator of photon. So this interacting displacement operator will displace it in the phase space. We can make the setup in such a way that the interval between two optomechanical interactions is a quarter of the mechanical period. Then we need to have 4 such interaction operators, and that 4 interactions operators will complete a loop in the phase space. And we know that if we have a complete rotation in the phase space, we will gain a geometrical phase. We will have some additional phase theta. And if we want to calculate that phase, we can simply look out the field operator. We calculate the mean of the field operator. That will give us the extra phase, and that is possible to calculate theoretically. Okay. Now, let us try to understand what we are trying to say here. So suppose we have a standard laser source, coherent laser beam here through, this is a reference one, and another laser source, we send it through the circuit where the laser light enters through the polarized beam splitter and electro-optic modulator, and it goes to the cavity to interact with the oscillator. Now, after interacting, it will come back and it will enter this path, and it will go back again to the cavity, and so on. Now we need at least 4 interactions as per the theory. Now after the 4 interactions, suppose we do not let the light enter within this path, but we just take it out. Okay, 4 interactions has already happened. We take it out and measure the phase that is obtained with respect to the reference beam we had. That will clearly show us what is the amount of theta. So this theta we have calculated theoretically can be measured experimentally. Now, if we can obtain a matching between the results of theory and experiment, then we can definitely say the oscillator is of the type that we have considered here. Okay, so the difficulty is here to actually build such an oscillator. But there are already a lot of possibilities nowadays. There are micromechanical oscillators, enharmonic oscillators. Those are all possibilities, and this is the task of the experimentalist to create, to design a perfect oscillator so that we have a matching of the results of the theory with the experiment. And once we have it, we can say that the oscillator we have created is a generalized oscillator, and the light coming out of that oscillator is obviously will be squeeze state. Like we can see this mechanism here. We consider. So if we send a light here, we get a squeezed light. So we can do the same experiment here. After having the generalized oscillator, we can use this setup to obtain a squeezed light for the generalized oscillator as well. Of course, you have to make sure that the noise is properly reduced so that the signal to noise ratio is greater than 1. And that we have made sure through the parameters that are available in the lab. For instance, the cavity finesse 0.1 is a very minimal one. We can have actually 10 to the power 5 order of the cavity finesse nowadays. So what we see here, that with the minimal set of the experimental parameters, the signal to noise ratio goes to 1. Also, notably, we have considered only n equal to 1. That means we run the experiment only one time. But we can do it multiple times to reduce the to increase the accuracy and to increase the signal to noise ratio and so on. So with that, let me go. I don't know how much time I have left. So, okay, so I think I can go to this direction as well. So the third thing that we want to talk about, the non-Hermitian model. Quantum mechanics is a good thing, we know, and it demands hermiticity. The observables demand hermiticity. But we also know nowadays that observables are not required to Hermitian. But what is required is these two conditions. So the reality of spectrum requires that any operator O is a symmetry of the antilinear operator, any antilinear operator. If it is symmetric with respect to that antilinear operator, as well as the eigenstate is a simultaneous eigenstate of these two operators. Then we will have real spectrum. That's all. For example, the PT-symmetry. PT is an antilinear operator, and here is a Hamiltonian. This is a non-Hermitian Hamiltonian for all values of the epsilon belonging to the real number, and this is also PT-symmetric. Here is a plot. We can see that the Hamiltonian has real eigenvalues when epsilon is greater than 0. But when epsilon is less than 0, we have finite number of eigenvalues, real eigenvalues finite number of, an infinite number of complex eigenvalues which merges together to appear in the complex plane. For instance, here you can see when we have discrete spectrum in the real plane and then it reaches to the exceptional point, and in the real plane we do not see them again because it has appeared to the complex plane. Now if you go to imaginary plane here, you will see that they will show up. So since it is a real plot, so we do not see them, it just appears in the, it goes to the other plane. So it means that though here we can say that this is PT-symmetric and non-Hermitian, so it should produce real eigenvalues for all the values of epsilon. But this is not happening here. We see that only when epsilon is greater than 0, we have real eigenvalues, but otherwise we do not have. And the reason is that we didn't consider the second definition, which is this one. Okay, so what we are trying to say is that even though the Hamiltonian is PT-symmetric, it does not guarantee the reality of the spectrum. But since PT is an antilinear operator, it may be possible that the Hamiltonian and the PT operator do not have simultaneous eigenstates. That is a possibility. If the PT operator and the Hamiltonian has a simultaneous eigenstate, then obviously the spectrum will be real. And that is satisfied in this epsilon greater than 0 region. In epsilon less than 0 region, the symmetry is spontaneously broken. And that's why there is no reality of the spectrum. So all what is these two conditions that are required for the reality of the spectrum. So let us try to understand how to realize this PT-symmetry in real life. For instance, we can think about a gain system and a loss system. So gain means that particles are going in the system, and the probability is not conserved, so it's a non-Hermitian process. The Hamiltonian can be written as A plus IB. And in the case of lossy system, the particles are constantly going out, and again the probability is not conserved, so this is also a non-Hermitian system. When we take these two systems separately, then the Hamiltonian, the combined Hamiltonian, is a non-Hermitian Hamiltonian. We cannot have real eigenvalues for such a system. But if we couple them through a coupling strength, let's say G, then the Hamiltonian can produce real eigenvalues provided that the G square is greater than equal to B square. That means if we can balance the system in such a way that the coupling strength and B is the kind of non-hermiticity we are supplying. So if this condition can be balanced throughout, then the whole system will behave as a real physical system. And when we can maintain this balance, that means the PT-symmetry is spontaneously unbroken. Okay. And there are some examples already where they have prepared PT-symmetric systems. The first one is PT-synthetic photonic lattice, where there is a gain system here and a loss system, and they are coupled to each other in such a way that the balancing is there, and that's why it's a PT-symmetric photonic lattice. Similarly, the toroidal shape microresonators can be used. For instance, this is a gain microresonator, this is a loss microresonator, and you couple them unidirectionally so that you have a PT-symmetric system, and this has been implemented on a silicon chip. So nowadays we have microresonator silicon chip, PT-symmetric chip, which can balance this gain and loss and so on. So here, what we have tried to do is that suppose I prepare a balanced gain-loss PT-symmetric system and let it interact with the environment and try to see the decoherence pattern for this interaction. So we consider a spin system, the standard spin system, PT-symmetric, of course, and the balanced gain and loss condition is satisfied when this alpha parameter is less than or equal to 1. This is simply coming from the eigenvalues. Eigenvalues are real if this condition is satisfied. So suppose we can prepare such a system, balanced gain and loss system, and we let it interact with a infinite number of bosonic oscillators, and we try to get the reduced dynamics of the system. What will come out, the process is like we have to evolve the composite Hamiltonian and then trace out the bath degree in order to have the system dynamics. And after having it, we will have the density matrix of the system is of this form. It is known that in the standard quantum mechanical case, we have these off-diagonal elements e to the power minus gamma t. Gamma t is a decoherence parameter. And because of these terms, there is a dephasing dynamics, and the system the coherence will decay out very fast. This is known. Okay. Now we have calculated this gamma t, the decoherence parameter, in this scenario, in the PT-symmetric scenario, and the expression is given. And one can check that in the Hermitian limit, the theta dependence goes away and it matches with the results of usual quantum mechanics. The understanding of the PT-symmetric PT-symmetric open system can be seen here in this graph. The first one, the purple lines correspond to the Hermitian system. This is a decoherence pattern for the Hermitian system. For the non-Hermitian systems, we have the orange line, red line, and the gray lines. What is here in actually this the pattern, the decoherence pattern is a periodic. It varies in between the orange and the gray lines. That is actually clearly visible from this plot. That if we try to see the pattern with respect to theta, it's a periodic in nature. So what we have to do, let's say we set the interaction angle to be pi/2, then we get the best decoherence pattern. And this is a great improvement with respect to the coherent one. We have lifted the decoherence up to a very good extent. If we look at the pattern of the decoherence with respect to the non-Hermitian parameter tau and with the time, we can see that again, when we take theta equal to pi/2, we get a very good pattern. It can actually asymptotically approach to the coherence limit. So we can recover the decoherence completely for such systems if we are careful in choosing the theta and the non-Hermitian parameter. Here, when we increase the non-Hermiticity, tau to be 50, then we get the best pattern, the decoherence, and so on. So now, if we try to understand what is happening to the entanglement in this scenario, the entanglement of formation, as we know, is a minimum amount of entanglement required to construct a correlated state. For a 2-qubit system, the entanglement of formation is a monotonic function of the concurrence. Therefore, if we calculate the concurrence, that will be the measure of entanglement for our system, for a 2-qubit system, which is our case. So if the balanced gain and loss PT-symmetric system is in a maximally entangled state and one of the spins has a dephasing dynamics, then it can be shown that its concurrence is exactly equal to the decoherence parameter. For instance, we can see here, this was e to the power minus gamma t was the decoherence parameter, and for a 2-qubit system, concurrence is exactly equal to that. So what it means is that if we can remove the decoherence, then obviously the entanglement does not die. It's a one-to-one correlation. So we don't have to study the entanglement separately, but removing the decoherence itself ensures that the entanglement does not die. And this is what we can see that in the PT-symmetric system, if we can maintain the balanced gaining and loss, as well as the interaction angle and the non-hermiticity and so on, then we can get rid of the decoherence. Okay, so with that, I would like to conclude that I have talked about 3 different things. The first one is the quantum resource theoretical framework to explore the non-classical properties of generalized quantum states. This is to say that generalization brings in an additional degrees of freedom, which is not possible to obtain from the standard quantum mechanics. So it's a non-trivial problem. If we can generate this thing, then obviously we have higher degrees of non-classicality. We have better resources. And using optomechanics, we have shown that it may be possible to generate such states, provided that the proper experimental setup explores the generalized oscillator. And also, we have shown that the non-Hermitian models can be less prone to decoherence if the balance of gain and loss can be maintained on the system. So with that, I would like to thank you very much for your attention.
This session is open for questions and discussions. Are there any questions in the chat box?
There is a question in chat box. So Narsimha want to know what is the order of coherence length of atomic laser? I think he is mentioning some slides in your presentation.
Okay.
The first slide, resources of atomic laser.
The first slide, you mean? Okay, so is it here? I didn't understand the question. Could you repeat it?
He want to know that what is the order of coherence length of atomic laser?
Oh, well, that depends. I think, okay, so here only. So obviously that depends on the type of atom we choose. It's a characteristics of the atom. The gap between the ground state and the excited state, that actually defines all the laser thing and so on. So yeah, in the standard case, it is entirely the characteristics of the atom.
I have a question.
Yes, please.
So, I have a question here. This the figure which you are showing, soft Poissonian photon statistics. I'm talking about that B.
Yeah. So here. Here only. These are the sub-Poissonian photon statistics.
And I go back to the previous one. Yeah, this is the one.
This
is the one. Yeah. See, in this figure B, where D is equal to 0.4, what is the physical origin of those sharp peaks and the envelope function? See, there's the envelope function as I could see in time, and there are these sharp peaks. Can you just explain?
So this is something related to the uncertainty of the system. So the system is actually not very stable in that region. So the main profile can be understood from this envelope actually. So these peaks are kind of a noise, but this is where the main profile lies.
I see.
So the non-classicality this is actually oscillating around the maximum value, which is -1. So this says that obviously the laser will be fluctuating due to the uncertainty principle around that point, and produce the envelope for atomic laser for the non-classical system.
Okay.
There is one more question in chat box.
Yes.
Can non-Hermitian models be useful for experimental purposes as they do not conserve probability?
Okay. So which model is speaking about? Because I have actually shown 3 different things.
I think he is asking about general non-Hermitian models.
Non-Hermitian models.
Asking about any specific.
Well, yeah, that is where all this formalism is important. So obviously, when we have a non-hermiticity, the probability is not conserved in that system. So in that case, yet we get real eigenvalues, and this model may not be generally completely true, but if the PT-symmetry is continuously unbroken, then it will be. Although, if you look at mathematically, probably the norm will not be conserved with the PT-symmetry, but then there are formalisms which are called CPT symmetry. Another charge operator comes in to recover the preservation of the norm. So if we introduce a charge operator, obviously if the Hamiltonian is PT symmetric, it will also be a CPT symmetry. So introducing a charge doesn't change any of the formalism here, but then the positivity of the norm will arise from that. So now if norm is positive, it's a physical theory. Obviously you have to replace the condition that the Hamiltonian is not Hermitian So H dagger H is replaced by H CPT equal to H. That's all. If we can do that, then all physical things are consistent in this scenario. And there is also an alternative formalism, which is also called pseudo-hermetism, where one can map a non-Hermitian system to a Hermitian Hamiltonian using a metric operator. And that metric operator, if you can construct, then obviously you are not working in the non-Hermitian regime. It's all about working in the Hermitian regime. And so they are all physical models that can come out for non-conservative systems as well.
So I have a question. Does if you operate locally PT-symmetric Hamiltonians on, let's say, only on Alice's side, then will be there any increase in the entanglement? And my second question is, I wanted to know your comments on quantum correlations like discord, entanglement, etc. in PT-symmetric quantum theory.
Okay. So the first question is that you said the locally PT-symmetric operations are done. And then what is your first question? Can you repeat it? So you are doing a local
Yeah, so if you, my
operations.
first question was, if you locally operate, let's consider a PT-symmetric Hamiltonian on, let's say, either of one side in bipartite system, then will the entanglement will increase or it will remain same as in standard quantum mechanics?
Okay, so you mean the entanglement, right? So, okay, you're talking about the non-locality or so on, right? So it depends actually. It may not increase at the first place, but when we introduce PT symmetry, you have to alter the whole system accordingly. So if you just apply, let's say, PT symmetric operation, and you just calculate the entanglement like the way you calculate the quantum mechanics, obviously it will not increase. I will say it will rather decrease. But you have to have a proper alteration of the corresponding things in order to recover that entanglement. So all what I'm saying is that quantum, it will not enhance anything from the quantum mechanics things, but it's an alternative to quantum mechanics. Okay, it's like a generalization to quantum mechanics. I don't know, because it's a hard question to say. One has to calculate really to see what is going on. Maybe at the end, if you fix things, you will get a higher entanglement, but it doesn't seem to me at the first place. Okay. Yeah. And the second question you had is regarding the correlation. Am I correct?
Yeah, a question regarding that quantum correlations in PT-symmetric quantum theory.
Regarding the correlations. Well, I think it is more or less the same answer will be. It is hard to say a priori whether the correlation will be satisfied if you consider it direct quantum mechanics, but you alter the system. See, it is not so easy, because wherever you apply this system, you will not get the preservation of norm and all these physical things. So you have to alter it accordingly so that you get all these things. Once you do it, things will be fine.
Okay, sir. Thank you.
Okay. Thank you, everyone, for your questions, comments.
So There is one more question by Kamlesh.
Okay.
How do we experimentally verify if the state of output light is a squeeze state?
Well, that is slightly explained here in this figure. So theoretically, we consider that if we send the light, standard desert light, through this setup that is shown here, there will be an additional phase theta that will be occurring, and this is the geometric phase, vary phase, that is gained by the system. Now, if this phase is obtained both theoretically and experimentally, that ensures that we prepare the oscillator. This oscillator, if we can do a proper engineering, we will have a matching, and that matching will ensure that this is the oscillator. Now, once we have the oscillator, the light coming out of the optomechanical system will be squeezed. Here is an example that we use the optomechanics to have a squeezed light. So obviously, if we have a generalized oscillator, that will also give a squeezing accordingly, and that's how we create the squeezed light for this generalized system experimentally. There can be many, of course, different other mechanisms, but it's a very open problem and it's a challenging problem. I have not seen anyone to approach this problem. This was the first understanding. It was not experimental understanding, of course, it's a schematic. We predict that if we have the matching, then we can, of course, get it. And there are actually a group of experiments that they are working on this problem. So this was, so I don't know whether, I mean, it takes time to understand these things experimentally, because this is a big result. If once get it, then it can actually outperform any quantum optical system. It will definitely give better non-classical states. So it's a long-term problem, but the beginning is that we have some understanding that these lights will produce this light.
So I guess there are no more questions. Are there any more questions? Anybody would like to ask more? So what is the, I am aware about this PT-symmetric systems in lasers and things like that. So this is an example where both phonon and photon are being used.
Right. Yeah, so in optomechanics, we use two degrees. So the mechanical degrees will create the phonon, and the cavity mode will give rise to the photons. Photon and phonon coupling happens here through these terms, actually, interaction terms. And this interaction is very little if we have a single photon interaction. Okay, and now we increase the number of photons through the driving. If we drive the system with, let's say, 10 to the power 8 number of photons, then we have a huge radiation pressure that deviates the movable mirror to a good extent. And because of that interaction, the mechanical influence will be converted to the optical influence. And that's how we study the optomechanical interactions. It's a very interesting field of research.
So which labs are engaged in this kind of work?
Many, actually. Assis Clark, McGill University, is doing optomechanics. Marcus Aspelmeyer in University of Vienna, they have a very good setup for these optomechanical experiments. In MIT, I've forgotten the name. There's a big lab in optomechanics.
Looking, by any chance, looking?
No.
Not looking.
No, I've forgotten the name. She is actually only working on optomechanics. Yeah, so there are many labs nowadays, mainly based on US and Europe. In India, of course, we do not have that much.
Okay,
Good
so
thing is that one can, I mean, nowadays there are experiments who are trying to bring everything in the room temperature, because generally you see the mechanical degree of freedom that needs some cooling in order to remove the thermal noise. Okay, but there are also papers who are saying that the whole experiment can be done in the room temperature. Now, if it's a room temperature experiment, then it's a very easy setup, right? We just have a oscillator and a light interacting with it.
that is right. That's right.
That's why it is probable that more experiments will come out.
Yeah. Yeah, these are the future of the next generation technology.
Yes, yes.
Yeah. So, Sanjeev, thanks again for a very nice talk, half theory and half leg on the experimental side. Very beautiful, very enjoyable. And so we thanks again, and we close the session.
Okay, thank you very much.